Okay, hi everyone, I'm Kevin, and today I'm going to be talking about the progress I've made so far for my research project. Okay, so basically the goal is to calculate the charge transfer rates for two models, interface 111 and interface 100. And this project is basically a spin-off from the Chemistry 676 class project I did last semester. If you guys remember, in the project last semester, I looked at 6 models. 4 of them, 2 of them were doped with sodium, 2 of them were doped with iodine, and 2 of them were not really doped. So the basic goal for that one was to see which PbTe nanowire was the best. And this is the same thing here. I'm looking at the charge transfer rate for both of these models, and I'm trying to see which interface would be the best. Okay, so the methodology for this is as follows. Basically, the first step would be to calculate the couplings for both interfaces. The first step would be to perform heating computations for both of them, and the second one would be to do molecular dynamics for both of them, and then finally I have to perform coupling calculations for both of them, and then after that I use the MATLAB code to calculate electron dynamics and charge transfer rates. Okay, so this is all the progress I've had so far. All couplings for interface 100 have been computed. I'm in the process of calculating charge transfer rates using MATLAB code. I have to learn more about how the MATLAB code works, mainly what the MATLAB code says and how to modify it. So I have to do that by talking more with you guys, such as Yulin and the professor. And then for interface 111, the heating and molecular dynamics have been computed, and I'm in the process of computing the couplings for interface 111. And for that, I have to learn how to modify the Voss code. When I'm trying to compute the couplings, I'm getting some sort of error messages. So currently, I'm trying to consult with people to learn how to get past that and to get the coupling files needed.
But as soon as couplings are ready, the rest of the process is easy for you, right?
Mm-hmm. Okay, and here are some of the preliminary results that I have. This is a position versus time graph that I have for interface 111. On the y-axis, we have the electron position, and on the x-axis is time. So this is just a preliminary result that I have for that.
Wait, what are the colors? What is the definition of color codes? What's the difference between blue and yellow?
let's see. If I remember correctly, yellow is an electron hole, or
Electron.
yeah,
And blue?
blue is the hole.
Mm-hmm.
All right.
So what do you see with, if you accept this definition? What do you see on how do you interpret this figure?
Okay. For the positive times over here, I guess at electron distance -10, there seems to be some sort of electron movement here.
Why at initial point of time electron and hole are located in different areas of space? And how do you create, what are your initial conditions? Like if the system is initially in ground state, there will be no dynamics, right?
Right.
So you do something, you perturb it away from ground state. So what do you do? How does initial state differs from the ground state?
So in the initial state, there's no movement, there's no perturbation, but then as time progresses, you introduce some light, so then the system perturbs into a higher state, right?
Yes, very good. But can you add a little bit more specifics? What does it mean, higher state? Like if you have occupied orbitals, unoccupied orbitals, like orbitals with electrons, orbitals without electrons, and then you have light. What happens after?
It's the electrons' energies changes from a ground state energy to a higher state energy.
Well, it's too global, but more mechanistic details. Does it take electrons from occupied orbitals? How many electrons? What happens?
So basically, from what I understand, the electron jumps from its ground state orbital to higher orbitals that were
Good. Just terminology from one of the occupied orbitals to one of the unoccupied orbitals, right?
Mm-hmm.
How does electron know from which orbital to which orbital it will jump?
How does electron know from which orbital to which orbital?
Mm-hmm. Like if electron is sitting on HOMO -10,
mm-hmm.
Does it know if the electron wants to jump to LUMO or LUMO +100?
Okay, so the way I understand it is that LUMO -10 has a certain energy associated with it, and the regular LUMO state has an energy to it. You take the energy for each of those states, subtract them, and then that's the difference in energy. So if the electron is LUMO -10, it'll need that difference between those two energy chains to jump to that higher energy.
So it needs to be in resonance with frequency of light.
Mm-hmm.
So those pairs of orbitals which are in resonance with light will be perturbed by this light, right?
Yeah.
Yeah. So you may want to like type it or explain it next time.
All right.
Good. So your initial state is a pair of occupied and unoccupied orbitals which are localized not in the same areas. Is your sample homogeneous? Which material do you are telling interface 100, but what is the material that you are studying? Is it like silicon or carbon nanotube or?
It's a PbTe nanowire.
Okay. Is it all atoms are lead and telluride?
No, it's they're doped.
Okay. So please next time mention it, because each talk is assumed as like fresh
Okay.
to ignorant audience.
All right.
Give all the details.
So I should assume no one has like any prior knowledge.
Exactly.
Okay.
Exactly. Exactly. It's rules of the game.
Okay. Okay, and then my final here is a three-dimensional graph. On the x-axis is my orbital index. On my y-axis also has an orbital index, and then on the z-axis is a position.
What? Position? Position of what?
Position of the electron. No, wait. I misread this. This is a frequency because it's seconds in inverse.
Okay, frequency. Frequency of what?
Frequency of that light photon that the electron absorbs to jump into the unoccupied orbitals.
Not very far, but not correct. A little different. So, can you go one slide back? So, why electron and hole are moving in space and in energy? We apply light only at the initial time, and then we switch like light, and then we put in a dark room, no light, and then it still moves somewhere. Why? What is the reason why electron and hole are moving in energy and in space?
Because when the light was on, it absorbed some energy from the photons around it, and then when we turn the lights off, the energy didn't go anywhere. The electrons still have that energy within it, so you'd expect for there to be some movement.
No. If the electron is in the eigenstate, it has some distribution in space that doesn't change. If we believe in quantum mechanics, then eigenstate doesn't change in time, right? So if you promote system into one of its eigenstates, there will be no motion. Energy will not change and position will not change. It will be some distribution but without motion. And you see drastical motion. Your electron and hole move by 3 nanometers, 30 angstrom. What is the physical reason for them to move? Which process you are hiding from us?
The thermoelectric effect.
Later, it's connected, but at lower level, basic, very basic process. So you do have your electronic states before you had a light that interacts with electronic states. What else exists in nature? What is the temperature of your? You mentioned you do molecular dynamics at you heating to certain temperature. Molecular dynamics and couplings. So what do they reflect? Which interaction they help to describe?
They help to describe how electrons interact with each other.
You do not need to heat sample. In ground state, electrons will interact with each other. It's a natural feature of any electronic structure theory. Why do you heat your model? When you heat, what does it mean, heat?
That means you're adding thermal energy to a material.
And what happens to nuclei, to atoms?
So in lower temperatures, it vibrates, and then when you add heat to it, it vibrates faster and faster. And then when you add enough energy, the
maybe not faster, larger amplitude.
Okay.
But yeah, yes, good. And how nuclear vibrations affect electronic states? Do nuclear motion affect? Does nuclear motion affect electronic state?
Yeah, yes, they do affect the electronic states.
Good. Please continue.
Okay, so if the nuclei had lower vibrational frequencies, then the electrons orbiting them will be in the lower ground state orbitals. But then if the nuclei were vibrating at a higher frequency, then the electrons surrounding it wouldn't be in the ground state orbitals anymore.
Well, right now you are telling story about thermoelectric effect itself. It's more complicated, and we are looking on a basic, like if there are two electronic orbitals, and there is a energy, same as you were describing photons. If there are two electronic states, and there is a photon that is in resonance condition, then photon may induce electronic transition, or electronic transition may induce emission of a photon.
All right.
Right? Same with atomic vibrations. If the frequency of atomic vibrations is equal to the energy offset between two electronic states, then it can either hit, induce absorption of energy from thermal to electronic, or there can be release, so from higher energy state to lower energy state.
All right.
And energy is dissipating into nuclear vibration. So we are not showing it in simulations, but we imply it in our heads that when this motion happens, sample is getting hot.
Okay.
It releases energy from electronic excitations to thermal vibrations.
All right.
Therefore, it changes energy, and both migrates in space. Make sense? Okay, so let's go to the slide where we stopped. So what are those frequencies?
So the z-axis is the frequency of the nuclei vibrating.
Not quite. Your first guess was that it is frequency how efficient electrons are moving from one orbital to another due to light. Repeat the same and replace light with nuclear vibrations. So just say it yourself.
Okay, so it's basically how electrons. It's the frequency at which electrons vibrate.
Rates. How quick electron goes from one orbital to another one.
All right.
Due to release of heat into vibration of atoms.
All right.
Okay. So this is two-dimensional object matrix. There are index on X, index on Y, and each skyscraper, which can be either tall or low, shows it has two indices, I and J. So if it is tall, it means from I to J it goes very efficiently. If it is low, it means from I to J it will not go.
Okay.
So some states will cool down quicker, some will cool down slower.
All right.
If it is the last slide, you may verbalize your conclusions or open questions that you want to address.
All right. And that's it for my talk. Are there any questions?
No. Wait. Summarize. Conclusions.
Okay, so in conclusion, I've just talked about my research and my progress thereof. Namely, I'm trying to calculate the charge transfer rates for two models. I've computed the couplings for one of the models. I'm having difficulty with the other, and I've just I've just demonstrated two figures that I've gotten from my research. Are there any questions?
Oh, let's thank Kevin for the effort. I do have questions.
Okay.
So let's go to your second from the last. Second from the last. Just go to the end.
6, I guess.
Yeah, this one. So, what are your plans? Do you plan to repeat this calculation for the same model again and again? Is there a reason to repeat calculation of this figure? Am I saying something silly, or it is, or there is a reason to repeat this calculation again and again?
Okay, so as I understand it, you want to repeat this calculation again and again for different couplings.
No, different couplings will be also very interesting, but it is expensive. With different, what else can you change?
With different initial conditions.
Exactly, exactly. This is like 2 minutes per each run. In one night you can accumulate data for a paper.
Okay.
And I hope you'll figure it out, but you can do it by next time.
Okay.
So just, do you remember which parameters in the code you need to update if you change your initial conditions? Which variables? Ask help from the club. Everyone knows.
All right, so I guess my initial energy and position.
Which variable? There are like 2 variables at the beginning of the code that you change manually. Look around, maybe someone wants to help you.
All right.
Check if David wants.
I don't remember what they are off the top of my head. It's I hole or I electron or IE, IH, something like that. I'd have to look at the code to find what the variable exactly is, though.
Yep, yeah, exactly. And what do they mean?
The initial position of the electron and the initial position of the hole. So
do not use word position. It's very confusing, especially for people with physics background. Like position is coordinate in space.
So it's the initial level.
Okay. Yes.
So if you have IE equaling 10, it would put the electron in LUMO plus 9.
Mm-hmm.
Because LUMO would be 1, HOMO would be 1, and then you're just adding on top of that or subtracting for HOMO.
Excellent. Yeah. So you just take the code, change these 2 variables.
Mm-hmm.
Right now they something like from HOMO minus 20 to HOMO plus 30, and change them by 1 and run again and record figure and numbers that comes out.
Okay.
And just by analyzing this data, you will learn something interesting and new, and it will be sufficient for a little paper.
Okay.
It will be both interesting for you, useful for community, and easy to do.
Got it.
More questions?
Maybe you already have mentioned it. What is this solid and dotted line?
Okay, so the solid line is the electron itself, and the dashed line is the electron hole.
Is the average?
Just whole, absence of electron. You
Okay.
wanted to say, right?
Mm-hmm.
What is the average energy?
Expectation value.
Oh, okay.
But it's not
But-
it's not energy, it's position.
It's position, right? But I'm just confused because of this blue line and green line. Green space is above and below this line.
Just by procedure, expectation value has only one value at each time. There is no forking here, even if
Oh, so this is the.
it's not the maximum of the peak. It's just expectation value,
Oh, okay.
like center of the distribution.
But yeah, that's make me confused. But because it seems like most of the population is around like -40, -50, that region. How is that average position of the expectation below is around 10? Around
There could be something near plus 50, but for human vision, there could be interference between orange and blue clouds.
Oh,
They
yeah.
kind of masking each other.
Oh,
It's more correct to do separate electrons and holes, but then it takes twice as more space and harder to analyze, and it's waste of space and
but yellow is then highest in a scale, maybe color scale, right?
It goes from dark blue to orange.
Orange, yeah, orange.
And one can normalize it so that neutral will be green, but maybe this normalization procedure was not taken care of in this specific case.
Yeah, but after the relaxation, after the like 1 or 10 picosecond, it look like it's localized on a very narrow region, like very bright orange region. But the average line is still way above and is slowly down.
It doesn't surprise me.
Yeah, that's-
In doped materials, the orbitals are not localized on doping atom, but typically take nearest neighbors.
mm.
Thanks for supporting discussion. Anyone wants to learn something from Kevin?
So another thing is, I don't remember actually your actual system because you already mentioned that you showed that as before, but I forget the X. So since it's interesting that it's flipping their localized position, how is your system look like? I mean,
Just
That's more-
explain by words or by hand waving what your system is.
how is your system look like? I don't remember exactly that.
You mean how what the nanowires look like?
Yeah, I mean, how is their geometrical feature something?
Okay. Well, one is a pure cylindrical shape,
Mm-hmm.
and the other is more of a, how do I describe it? Helical-ish shape. I don't know how to like describe the shape of that system. Yeah, I should have put a picture up here.
So it also has symmetry in the z-axis?
Yeah, all my models are symmetric on the z-axis.
How many atoms is in your system? Well, it's hard. No one is expected to remember, but roughly, is it like 5, 10, 100, 1,000, maybe 200, maybe 300? Approximately, what's your last number?
Hundreds.
Okay, a couple hundreds.
Mhm.
And how close or how far lead and what is the stoichiometry? Is it like lead 2 telluride 3, or it is 1-to-1 ratio?
1-to-1.
Okay.
So it's about 100 atoms in like 9 nanometer thickness?
So how far is one lead from 1 telluride? What's the interatomic distance? Roughly, do not...
I'd say about 1 or 2 angstroms.
But 1 or 2, because Jebet is asking, is curious, typically for hydrocarbons or for carbon-based materials, the carbon-carbon distance is like 1.4, 1.5.
Mm-hmm.
And if you assume that your several hundred atoms have 1.5 interatomic distance, then the length of your nanowire will be maybe like 30 angstrom.
All right.
And if it is almost 100, it should correlate to either you have very thin nanowire or interatomic distance is substantially bigger. It's maybe like 3 or 4 angstrom. Do you remember something like this? not now,
Oh.
but you may check
All right.
because it's not usual for conventional materials on one hand, but on another hand, those are heavy elements with large ionic radius, and it is not a big surprise that interatomic distance is a little bigger.
All right.
This is not a discovery, but it's interesting technical information that some experts could be interested in.
So I'm just curious because what is confined in X and Y directions? What is the longest dimension? Z is the longest dimension in your system?
Yeah.
You're saying the nanowire is because one dimension is comparatively longer compared to other two.
Yeah. The Z dimension is definitely
Is the
longer.
longest.
Yeah.
So it should be Z direction. It should be periodic in that case.
Exactly.
Then what is the significance of this figure? Because it plotted it to the Z projected in Z.
Ask Kevin
Oh,
a question that he was already answering.
no, it's not actually a
Ask him-
question. I'm just
no, no,
wondering. Yeah,
just
I'm
for
curious.
learning, not to check his knowledge, but for your curiosity.
Yeah.
Ask him if the system is homogeneous. Are all atoms lead and telluride, or there are any impurities?
Oh.
No, ask him and listen
So-
to it.
There are some impurities in there. But both the models I'm studying have been doped.
Oh, so if they have some impurities in Z direction, so that's why it's also important to look on the localization in Z axis, although it's periodic. So what is the length of X and Y axis? I just want getting some idea about your system here. So it seems like your Z axis is about 190 or 100 angstrom.
Mm-hmm.
How long is your X and Y axis?
What's the diameter?
What is the diameter in other cases?
If your nanowire is cylindrical, what is the diameter? What is aspect ratio? Roughly. It's,
Roughly, not exactly. I'm just
is
trying
it,
to
like,
get some
is it
idea
like
of
1
what
to
it
2 or 1 to 100 or 1 to 10?
Oh, you mean the ratio of the X and Y axis compared to the Z?
is.
Yes,
Z axis,
yes.
yeah.
Alright, I'm gonna
Just
guess-
visually, you can remember. Like,
What?
maybe in your memories you remember how it looks like. and-
maybe 1 to 50, 1 to 60. That'd be my rough guess.
A little less ambitious, maybe 1 to 20.
Any other questions?
So, which model specifically is this? You say you have
Uh,
two different doped and non-doped,
This is for the interface 100.
but is this model one of the doped models you were looking at, or
You mean like?
you said you had iodine doped, non-doped, and
That was
Third
that was
dopant
for
that I
my
don't remember.
class project. Here I'm looking at two somewhat similar but different models.
So to save time, instead of doing meticulous screening of all possible versions of the material, he's looking on most important, when there are both doping simultaneously,
okay.
and they are responsible for this vivid charge transfer. Without doping, it will be like boring, homogeneous, like the whole figure will be like homogeneous color
Yeah.
without any change.
What's the meaning of interface here? Because usually when you have interface, that means you have two different materials, right? And they just touch with each other, so you have interface. So what's the meaning of interface here?
When you're saying 111 and 1000, what is the difference in your system in these two cases?
Are they doped differently, or they are oriented in space differently? Like, good question.
Okay, so from what I'm guessing, so the 100 and the 111, it's referring to their shapes, how they're shaped differently. So in response to your earlier question, I said one of the configurations was purely cylindrical shape, and the other one was somewhat helical shape. So so the 111 and the 100 is referring to that.
Which direction is nanowire is growing? Is that so? It's not a doping.
The index 100 and 111 doesn't relate to doping. It relates
Is
to
it growing?
And the best expert to help in this question is Fatima. She's publishing papers on nanowires grown in different directions. So she probably is best educated of all of us how to explain what is this, what are those indices.
Any other questions?
I have a question. Why these exponential fitting lines overlapping, like crossing? Is it?
All right. Sorry, can you repeat your
There
question?
are two exponential fitting lines for electron and hole, right? Why they are crossing?
Why these two lines are crossing?
Mm-hmm.
Look on their position of initial and final states.
Okay, so here's the yellow line. This fate yellow line here is the position of the electron. As you can see that as time changes, the position of the electron changes from here to there.
If you're not satisfied, keep asking him. That's his
I know
responsibility.
the electron should be relaxed at the LOMO and hole should be.
Here is
This
position.
is
What is your
yes,
axis?
yeah.
How your label axes are labeled? What is your y-axis?
My y-axis is in interatomic distance.
Is it introduced?
Coordinate, position.
Okay.
But some of us from previous practice may think that your y-axis is energy.
Okay.
Can you certify that it is not energy but position?
Yes, it's not energy, it's position.
Good. More questions? Okay, if no, thank